Hello and welcome to Cruising Through Calculus. My name is Alex and today we're going to be looking at problems about estimating areas. So let's dive right in. Our first problem says, approximate the area under the curve over the given interval using 4 left endpoint rectangles. And then they give us a function and an interval. So when you're doing this problem, the first thing you want to do is figure out what is the base of each rectangle using the delta x formula, which is b minus a over n. So in this problem, this is going to be 1 minus negative 2 over 4, because there are 4 rectangles they want. So that's going to be 3/4. The next thing you're going to want to do is you're going to want to draw out 4 sub-intervals here, like this. These are going to represent our 4 rectangles here. And we're going to start at negative 2, and we're going to end at 1. And what's going to happen is we're going to increase by 3/4 each time. So if you do negative 2 plus 3/4, you get negative 5/4. So we're going to go from negative 2 to negative 5/4. Then we're going to go from negative 5/4 to the next point, which is, well, we're going to add another 3/4. So that's going to give us negative 1/2. Then we're going to go from negative 1/2 to the next point, which means we have to add another 3/4, which gives us a 1/4. And then finally, if you take a 1/4 and you add 3/4, you end up with 1. So in this particular problem, they wanted us to use 4 left endpoint rectangles. And this is why I like to set it up this way, because the left points are the ones that we're going to be picking here. So it's pretty obvious which of the points are that we need to pick. It's these ones here. So what we're going to do is we're going to take each of these points and we're going to plug them back up into our function up here. This will give us the height of each rectangle. So let's start with the first one. Okay, now this one isn't too bad because it's going to be 9 minus 4, which means we're going to get the square root of 5. Over here, and from this point onwards, I just decided to plug these into a calculator because they aren't very nice, as you'll see. So this next one is the square root of 119 over 4. Remember, this is what you get if you take this value, plug it in here for x, square it, and then do 9 minus that, and then take the square root of that. Let's take a look at the next one. What happens if we take negative 1/2 and plug it in here? We get root 35 over 2. And then finally we have a 1/4. So if we plug that back into here, we get root 143 over 4. Ooh, not the nicest. But that's okay, because these are the heights of all of our rectangles, and we know what the base is of each rectangle. So if we want to estimate the area, all we have to do is the base times the height, plus the base times the height, plus the base times the height, plus the base times the height. And you'll notice that the base is the same each time. So when we go to do our area formula, what I'm going to do is think of it as like factoring 3/4 out, and I'm going to add all of these up now. So we got the square root of 5 plus the square root of 119 over 4 plus the square root of 35 over 2 plus the square root of 143 over 4. And by the way, that's all over 4. The square root is only part of the top piece. And then this is what I'm going to plug into the calculator. Now I've already done that, and what you get is 8.183. And so that is our final answer. Here is a graph with the shapes put in so you can visualize the areas that we were finding. Our next problem says, for each problem approximate the area under the curve over the given interval using 3 right endpoint rectangles. So the process is going to be very similar to what we did before. The first thing we do is we find our delta x, which is b minus a over n. In this case, we have 3 rectangles, so n is 3. And a and b are always based off the interval here. So that's how wide each rectangle is going to be. Next, what we're going to do is we're going to draw in 3 sub-intervals here. We're going to start at 1, we're going to end at 3, and what we're going to do is we're going to increase by 2/3 each time. Because this is the base of each rectangle has to have a base of 2/3. So if you do 1 plus 2/3, you get 5/3. Then you go from 5/3 to the next point, which is another 2/3, which is going to be 7/3. And then if you take 7/3 and add 2/3 to it, you get 9/3, which is 3. Now, because in this problem they want us to use right endpoint rectangles, that means we're going to choose the rightmost point. These are the numbers that we're going to plug back into our function up here. So let's see what happens when we take 5/3 and plug it in. Now, I've already done this ahead of time, mostly because you don't get very nice answers. You get 173/54. Let's see what happens when we plug 7/3 in. Again, I've done this ahead of time. 283/54. And then finally, y of 3, which you think would yield a nice answer, because it's 3 you're plugging in instead of just a fraction. But it's not the nicest answer in the world. It's 19/2. These are the heights of each of our rectangles. So now what we need to do is do base times the height, plus the base times the height, plus the base times the height. And since the base is the same for each and every one of these, we can take that 2/3, we can factor it out, and we can add these together. Finally, plugging this into a calculator gives us our final answer, 11.963. And that's our answer. Here is a graph with the shapes put in so you can visualize the areas that we were finding. Our next problem says, approximate the area under the curve over the given interval using 5 midpoint rectangles. All right, so we start off doing the same thing we've been doing this whole time. Let's figure out delta x. So b minus a over 5 midpoint rectangles. So that's going to be -1 plus 6, which is 5, and 5 divided by 5 is 1. Okay, that's nice for us. Now what we have to do is draw out 5 of these. And we're starting at -6, and we're going to end at -1, and we're going to increase by 1 each time. So this is going to be really easy. No fractions involved. Didn't even have to worry about doing this beforehand to make sure I get all the numbers right. Okay, now this part is different though. Because we want the midpoint, that means we want the middle of each of these. So what's in between -5 and -6? Well, that's -5.5. And we have -4.5, -3.5, -2.5, and then -1.5. For these ones, it was pretty easy. Keep in mind that if you get some numbers that are nasty, what you want to do is take the two numbers, add them together, and divide by 2. And that will give you the midpoint. Okay, now what we have to do is take these here and plug it back into our function. So for the first one here, we get -5 over -5.5. Over here, we're going to get -5 over -4.5. Then we're going to get -5 over -3.5. Then we're going to get -5 over -2.5. And then we're going to get -5 over -1.5. So in other words, and these will all turn positive, by the way, but these are all the heights of our rectangles. So to find the area, we just do base times height plus base times height plus base times height plus base times height plus base times height. We have 5 of those. The height is just 1, though, so I don't even have to worry about it. So really what this boils down to is 5 over 5.5 plus 5 over 4.5 plus 5 over 3.5 plus 5 over 2.5 plus 5 over 1.5. So if you plug all that into a calculator, you get your final answer, 8.782. And that's our answer. Here is a graph with the shapes put in so you can visualize the areas that we were finding. This problem says, approximate the area under the curve over the given interval using 4 trapezoids. So this one is going to be a little bit different because the formula for a trapezoid is different than the formula for a rectangle, at least when we're finding areas. However, we start off the same way. Let's figure out our delta x here. It's going to be b minus a over, and then it was 4 of these. So that's going to be 6 over 4, or 3 halves. Now what we're going to do is we're going to draw out 4 subintervals. So these will be the sides, or the bottom parts of our trapezoids. We're going to start at -2, we're going to end at 4, and we're going to increase by 3 halves each time. So -2 plus 3 halves is -1/2. Then we go from -1/2 and we add another 3 halves, which gets us up to 1. Then from 1 we add another 3 halves to get us up to 5 halves. And then 5 halves plus 3 halves is 8 halves, which is 4. Okay. When we were doing the left and right and midpoint rectangles, what we would do is we would just pick either the left or the right or the midpoint. But this is a trapezoid we're dealing with here, which has a different formula. So the formula for the area of a trapezoid is going to be like this. The area is going to be, let me write it out over here, 1/2 times the width of the trapezoid times f of x1 plus 2f of x2 plus 2f of x3 plus f of x4. And I'm stopping at 4 because we have 4 of these that we're doing. So you'll notice that the middle pieces have 2 and 2, but the first and last piece don't. The reason for that is because if you look at the way we've drawn this out here, check it out, there are 2 of each of the middle pieces. Meanwhile, there's only 1 of the beginning piece and 1 of the end piece. So what we have to do is take these numbers here, -2, -1/2, 1, 5 halves, and 4, and we need to plug it into our function here. Then we need to plug everything into this formula over here. So let's go ahead and do that. Let's see here. If we take -2 and plug it back into our function, we get 5. If we plug -1/2 back into our function, we get 95 over 16. I've already done this ahead of time. If we take 1 and plug it back in, we get 23/4. If we take 5 halves and plug it in, we get 71/16. And then if we take 4 and plug it back in, we get just 2. So now we have everything we need. Our area is going to be 1/2 times delta x, which is 3 halves, times 5 plus 2 times 95 over 16, plus 2 times 23 over 4, plus 2 times 71 over 16, and then plus just 2, like this. And you know what? I realized something over here when I was writing this out. I didn't write it out correctly. I said we stopped here because that would give us 4, but actually we need this to be 2, and then we need to have one more here, a 5th point. Because there are 1, 2, 3, 4, 5 different points that we got along here, starting at -2 and going up to 4. So this formula down here is correct. The only thing left to do is just to plug it into like a calculator, which I've already done. You get 29.438. And so that is our final answer. Here is a graph with the shapes put in so you can visualize the areas that we were finding. This problem says, use a left-hand Riemann sum to approximate the integral based off of the values in the table. So they want us to estimate the area of the function from 0 to 8 using the data in the table and using a left-hand Riemann sum. So the process is going to be a little out of order from what we did last time, but essentially the same. The first thing we want to do on this one is actually start with our intervals. So 0 to 2, 2 to 6, 6 to 7, and then 7 to 8. Then using this, we're going to figure out what our delta x is. So what is the base of each rectangle? Well, to get from 0 to 2, that is going to be 2 units long. So that means that the base of this rectangle is 2. The base of this rectangle here is going to be 4. And then the base of the final two rectangles are both going to be 1. So notice that the delta x is different for each rectangle. If we were using the b minus a over n formula, then we would get the same width or the same base for each rectangle. But since they just gave us seemingly random points here, it's going to be a different base for each rectangle. Okay, next, they said to use a left-hand Riemann sum. So that means we have to take these points and we have to plug them back into our function. Now normally we would plug it back in and maybe we would use a calculator to get the answer, but take a look. They tell us what happens. If you take 0 and plug it in for f of x, you get 4. If you take 2 and plug it in, you get 2. Take 6 and plug it in, you get 3. Take 7 and plug it in, you get 2. So these are the heights of the rectangle at these points. Now we just need to do base times height plus base times height plus base times height plus base times height. This time, the base is different for each one, so I have to write it out for each and every one. So 2 times 4 plus 4 times 2 plus 1 times 3 plus 1 times 2. So let's see what we get here. This is 8, this is 8, this is 3, and this is 2. 16 plus 5 gives us 21. So that's our final answer right over there. Our next problem is similar to the last one, but this one says use a right-hand Riemann sum to approximate the integral based off of the values. So we're going to start off doing the same thing. We're going to go ahead and write out all of our intervals, so from 0 to 2. And you know what, while I do this, let's go ahead and find the delta x of each one. From 0 to 2 means our delta x is going to equal just 2. Then from 2 to 3 means our delta x is equal to 1. Then from 3 to 13, our delta x is going to equal 10. From 13 to 16, our delta x will equal 3. 16 to 17, our delta x will equal 1. And then 17 to 18 is also going to be 1. Let's see here, 17 to 18. Now, because we're doing a right Riemann sum this time, we need to pick the rightmost points. These are going to get plugged back into our function. And can you see what they are going to be? They're going to be these points here. The ones all on the right side. So when we go to add everything up together, all we need to do is base times height plus base times height plus base times height. Let's see here. 1, 2, 3. Then we have 3. Let's make sure I'm getting this right here. It's 8, 7, 5, then 2, then 5, then 4. There we go. Okay, so I already added this up ahead of time into a calculator. You get 88, and so that's our final answer. I wanted to go over the procedure that I'm following when we do problems like these. The very first thing we have to do is to find delta x, and almost always that means using this formula here, b minus a over n. If they give you a bunch of information in a table, you have to find delta x using the table. You'll do this by figuring out what it takes to get from one x point to the next x point. After you do that, go ahead and write out all the intervals. Now, once you have your intervals written out, you have to pick either the left, the right, the mid, or both of the points, and then plug them back into your function. Now, this depends on what they're asking you to find. If they're asking for a left Riemann sum, you're going to choose the left points on your intervals. If they're asking for a trapezoidal sum, you're going to need both points. In either case, once you have picked either the left, right, mid, or both points, you have to plug them into the correct formula, which is either the rectangle formula, which is just base times height, or delta x times your f of x, or the trapezoid formula, which is 1/2 delta x and then f of your first point plus 2 times f of your second point, and so on until you get to the last point. After you plug it into the formula, it's just as simple as figuring out what all of that math adds up to, and you'll get your final answer. If you found this video helpful, you might consider checking out my website, which is linked in the description below. You'll be brought to Infinity Learning Academy, where you can find Cruising Through Calculus. At Cruising Through Calculus, we have over 100 videos and documents to help you get through your calculus class, including videos for each topic, practice problems, and full video solutions for those practice problems. I hope to see you there, and together we can cruise through calculus.